So this week you'll continue working on functions and pass by reference and everything that we've covered over the last couple of weeks. But today we'll move on to the next module, which is arrays and collections. And again, we'll start and focus on C at first, because when we get over to Java, much of the stuff that we cover in C is either going to be applicable, or the way that I cover it is we're going to throw it all away and use something much better. Dynamic data structures like lists, sets, and maps that Java has that C does not have. So this will probably be the first major module in which, pointers are of course a major difference between the two languages. But this will be the first module where there's another major difference in that we also have garbage collection. So memory management is something that we'll have to worry about in C. It's not something we have to worry about, or we can't even do anything about it in Java, because it's all handled automatically. So the motivation for looking at arrays and more generally collections, right, is that you almost never deal with one piece of data. Instead, you deal with a collection of data. There's not just one score. There are 50 scores or 100 scores, and you don't know up front how many pieces of data necessarily that you're going to be processing. In both C and Java, we have arrays, which are collections of similar things, right? Things of the same type. In other words, when you have an array, you have an array of integers. When you have an array of doubles, an array of characters, but you don't have an array that holds both doubles and integers and characters at the same time. There are languages that support that. They're called mixed types. It's almost never a good thing, but you do have languages that support that. Neither one of our languages do, though. In general, in both languages, in fact, in every language that I've ever seen, arrays have a single name identifier, right? You access individual elements using an index. An index is simply just a number. It's kind of like an ordinal, but it's a zero indexed. Arrays always are always zero indexed. Right? That means that the indexing starts at 0. And we've seen this before when we try to access the arguments in an array. In both languages, args or argv, right? We start at argv sub 0, argv sub 1, argv sub 2. And you use square bracket notation to access them. Right? So for example, if I have an array of integers, ARR sub 0 is the first element. Right? Where's the second element? ARR sub 1, right? ARR sub 2, right? Etc. So the first one is already always at 0. And there's a very good reason for this. We'll cover that reason later on. It's because that's how memory works. These indices are actually an offset that the compiler compiles the memory address given that index and given the original memory address of the array. And so 0 indexing ensures that the math works out. Right? If an array holds n elements, then the last element is at where? My array ARR, I'm not being inventive there, ARR is just short for array. So if there are n elements in that array, where's the last one? N minus 1, exactly. You always have to be thinking in zeros, right? So in computer science, we all start counting at 0. In fact, real mathematicians started counting at 0 too. Why? Right? If you don't have 0 in your, so the set of natural numbers, right? You might have seen this before, right? That's the set of natural numbers. Where does it begin? Careful. 0, 1, 2, 3, ... If you only start at 1, then those are the counting numbers, right? And that's the grade school way of thinking about it. You need 0 because you need an additive identity. X plus 0 gives you X, right? You need that 0 in order to form a group or a semi-group or something, whatever it is, right? I forget off the top of my head. But in any case, let's go ahead and start taking a look at arrays in C. Right? We're going to start with what are called static arrays. Right? And the static here, static in this case means that they have a fixed size when they are created and they are allocated on the stack. Right? So this is how we're going to start with arrays, and then we're going to quickly move away from them, and I'm going to demonstrate why. All right? So let's come over here to the code demo. And oops, yeah, remind me later about that. I'll get rid of that, get rid of that. And here's my demo code. Give myself some more room here. Right? Get rid of that. Sorry, I should have cleaned all this up before I got here. There we go. All right, so let's go ahead and create an array. Create an array of integers that holds up to 10 elements. Right? So I'm going to say that it's an integer array. If I just said ARR, how many elements is that? 1, right? That's one integer. So I'm going to specify the size. Oops, we said up to 10 elements, right? So within this bracket notation, when you declare the array, you can specify its size. Now, it can hold 10 things. What's in there right now? What is stored in ARR right now? Right. Let's find out. For int I equals 0, I is less than 10, I plus plus. Let's go ahead and print out the contents of that array. Array sub %d is equal to %d and the line. I'm going to print out both the index I and the element stored at that index I. Right? So it doesn't have to be 0, 1, hard-coded index values. It can be a variable like in this case. Okay? There's my idiomatic for loop. This is why I called it an idiomatic for loop to begin with. Anytime that you're going to iterate over an array, a for loop. Why? Because you know exactly how big that array is. So for I starting at 0, strictly less than 10, the size of the array, gives you the exact functionality that you need to iterate over those elements. Let's find out what's in there. What do you think's in there? Maybe 0? Or dead beef, garbage. Exactly. Uninitialized memory is uninitialized memory, right? What's in there? Whatever happened to be in there prior to you actually creating this memory, right? So you do have to be careful, right? What's in this array right now? Garbage, right? As we've just seen. So let's go through and actually assign things to it. Right? Well, I can print it out by accessing it. So let's go ahead and assign a value. I is equal to, I don't know, I plus 10. There we go. And now let's print it out again. Right? What values did I assign there? Let's see, 0 plus 10 is going to be 10. 1 plus 10 is going to be 11. So 10, 11, 12, 13, 14, dot, dot, dot. What's the last one? 19? Good. Right. And remember, it's going to be indexed 0 up to 9, where 10 is the size of the array. Let me jump all the way down here. I forgot how big was the array? 10, right? Because nobody's that forgetful. But come back, a week from now. Did I use 5 or 10? Right? Is there a way to tell? No. There is 0 way in C to tell how big an array is. You have to do the bookkeeping. In other words, we shouldn't have hard-coded this value. We should have put it into a variable so that we can access it later on. You can do this, but shouldn't. But again, we're going to get away from static arrays very, very quickly. For anybody with prior Java experience, this will be completely new and surprising because in Java, you can tell how big an array is. The dot length property. In C, no. You have to, it's on you to do all the bookkeeping yourself to keep track of it. Right? So put it into a variable. All right? Okay. Let's put this over here so that we can have some demo code in our handout, or in our example here. Let's go ahead and take a look at a visualization. Right? And let me zoom in. Here we go. In fact, I just talked to Philip Guo, the guy that created this. He made an announcement that he released a new version of it. And there are slight little changes here and there, but like the new AI help here. But I sent a note to him and I said, hey, great tool. I've been using it for like 7-8 years here. Right, so it is a great tool, pythontutor.com, if you ever want to visualize your code. And of course, again, it's not just Python, it's C, C++, I think Java too, etc. Right. So let's walk through this. I've got an array here. I didn't make 10 because it'd be really large, right? But let's go ahead and walk through this as I assign values to it. Right? First of all, I said that it was allocated on the stack, right? Meaning that it's in the same stack frame as this main. So think about this, think ahead about this. What if I create an array inside of a function? Remember, stack frame on top of stack frame on top of stack frame. If I create an array inside this function and I return back from that function, what happens to the array that's stored in there? When it gets popped off the top? Bye. It's gone. It's destroyed. Right? So let's go ahead and walk through this and see how it changes. Right? The other observation from this visualization that I want to show you is that they're all contiguous. Right? It's all stored right there together. Right? That's how arrays work. The first element in memory is right here. The next one right after it is right next to it in memory. It's not in some random location somewhere. Okay? They're all right together. This has an implication for creating large arrays. Let me go ahead and create another array here of, I don't know, int n is equal to 1,000. Right, there we go. And then I'm going to make sure that the compiler doesn't get rid of my stuff by actually using it. Arrays of 0, I'll set that equal to 42. And arrays of n minus 1, remember the last element, you told me it was n minus 1, right, is going to be 101. And then we can print it out or something. I'm not going to go that far. That's all I need. Right? This will work just fine. Right? Maybe I do want to print it out because I want you to see that it actually works. Arrays of 0 is equal to %d and the line, and arrays of 0. I am actually setting these things. What about all the rest of them, by the way? What about all the 998 other values in here? Just garbage, junk. But now that I've set those two, of course, I'm going to get 42 and 101. That's 1,000 things. Tell me, how much memory is that? Hint, there are 4 bytes in an integer, so therefore 1,000 of them would be 4,000 bytes. That's a little bit less than 4K, 4 kilobytes. 1, 2, 3. 1 million bytes times 4 is how big? 4 million bytes. That's 4 megabytes now. Right? Let's see if this still works. It does. 4 megabytes. Let's go up to, I don't know, 2 million integers, which would be 8 million bytes, about 8 megs now. Okay. Oh, it still works. Come on. All right, let's go up to 10. So how many is that? There we go. So 10 million, that's 40 megabytes, a little less than 40 megabytes. Is that big data? No, I mean, pull out a thumb drive and you've got what? Gigabytes, right? This is nowhere near big data. But we get a segmentation fault. Why? Remember what I just showed you? That it's actually allocated on the main. Right? Let's go ahead and edit this code, and let's bump this up to 5. I only need 5 million. 1, 2, 3, 1, 2, 3. 1, 2, 3, 1, 2, 3. Okay, there we go. All right. Let's visualize this. All right. So, tell me what that stack is even going to look like. Oh, wow. Okay. That array inside that stack. It's going to be 5 million things long. There we go. It's not even going to let you do something like this, right? Because I imagine that it's actually dying in the browser because it's not able to render 5 million things long, right? What's happening over here? My stack space, remember, you've got stack space, you've got a stack frame on top of stack frame on top of stack frame. Well, you only have one stack frame, but how big is it? 10 million times 4, 40 megabytes. Right? That's too big. Right? That's going to result in a stack. What happens when we put too much in the stack? It overflows, stack overflow, and that's exactly what's happening here. In fact, I can detect if I go ulimit stands for user limit, and then I ask it about everything. Where's the stack size? There we go. This is in kilobytes, so 8,192 kilobytes would be about 8 megabytes. Can I do 40 megabytes? Nope. So stack space is very limited. It's only 8 megabytes in this case. Usually it's like 4 megabytes or something. It's measured on megabytes. In fact, if you go to an embedded system, right, where it's just a very simple system, it's not a full computer like an Arduino or something like that, you might have even smaller stack space measured in kilobytes instead. This is why you have to be very, very careful with static arrays. Right? Since static arrays are allocated in a stack, they exist within one stack frame. Stack frames are limited. Stack space is very limited. Right? It's 4 megabytes or 8 megabytes or even kilobytes. Right? You cannot fit even a moderately large array on the stack. You cannot fit even a small array on the stack. Right? Small here is going to be in double quotes here because, if there's 5, 10, 15 things, okay, who cares, right? But you have to be careful. In Java, static arrays are not even possible because of this reason. They do not allocate anything on the stack space because they know the stack space is precious. And it doesn't even allow you to abuse the stack space like this. Let me show you. Let me bring this over here to Java. Right, there we go. In fact, I don't even need to print things out. Am I able to do this? Nope, it does not compile. Let me go ahead and put this into hard-coded value here, right? Okay, well, that's too big. Maybe Java's just saying, okay, that's too big. No, you can't even do small arrays like this. Right? You have to what's called dynamically allocate them, okay? Before I show you that, dynamic arrays, let's look at some other syntax. Right? So get rid of this. There we go. You can create and initialize small static arrays like the following: int primes. All right. Let's go with the first 10 primes. Let's see if we can figure them out. 2 is prime, 3 is prime, 5 is prime, 7, 8, 9, 10, 11, 13. Am I missing any? 17, 19, and what am I up to? 8, 23, 29? 27 is divided by 3. So I think I got them all. Did I miss any? Did I get 10 of them? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, let's go one more, 31. I got too many of them, right? There, it'll detect that. Wait a second, you tried to create an array of size 10. You gave me 11 things. Right? I'm a dumb compiler, but I can count the number of commas that you put into this thing. And so it's able to say, nope, you can't put 11 things into something of size 10. So it's just a warning, by the way, right? You're screwing up your own memory. You can go ahead and do whatever you want, right? But it's going to be a warning, and I'm not going to be able to do that. So this is a way that you can statically create an array. In fact, a dumb compiler can still count. You don't even need to put the size in there. Right? It's called, here's your 50-cent word for the day, elision, to elide something. So what does that mean in language? So if you just run a bunch of words together, right? Native speakers do this all the time in any language. Like if I say, did you go to lunch today? I said, did you go to lunch today, right? But I didn't say that. I said, ja, right? Did ya? All right, I ran that all together. I elided away a bunch of syllables, or syllables, in order to speak faster, more natively, right? And this is elision in programming. That's not necessary. A dumb compiler can go ahead and count the number of commas and be done with it. So you can elide that away if you want. It's optional, right? What happens when we do things that we shouldn't, right? So let me go ahead and go with prime sub 10 is equal to 31. Am I going to be able to do that? Right. What's going to happen here? There's only 10 things in there. What's the index of the last one? 9. So I'm trying to access something that doesn't belong to me. Or likewise, can we have negative index values? Not in C, not in Java. In plenty of languages you can. Right? What happens is, like in Python, what happens if you've got 0, 1, 2, 3, 4, and you go 5, it wraps around. If you go negative, it wraps around the other way. Or there are ways of doing that. Not in C, not in Java. Let's see. Will the compiler tell us about this? Let's find out. Oh, well, it will if I don't do something. 31, 33, 30, 35, 36, 37. There we go. There we go. Compiler's dumb, right? They're not going to be able, maybe, oh, there. The warning is that you haven't done anything with it, right? So the warning won't even come up that I'm accessing stuff that doesn't belong to me. Let's go ahead and find out what happens. There we go. A stack smashing event. What have we done? Remember, it is allocated in the stack. Let me kick this down so that I could have a successful visualization here, right? So what has happened here? If I tried to access something outside this array, what memory am I accessing? The stack. That's my stack. I can do whatever I want with it. But if I start going mucking with things like I, or whatever's below the stack or above the stack, right? A good operating system will say, wait a second, you're screwing up your own memory to the point that you're destroying your own stack here, right? I'm overriding with whatever code happens to be in this stack with 31 or 37, right? And it detects that and it kills it. Right? What if I just went, outrageous? Right? Let's go ahead and get rid of this because that's probably the stack smashing event. There we go. It was not able to detect that I was smashing my own stack because it was way beyond the memory address there. But it's still a segmentation fault. I'm accessing memory that I should probably not be accessing. As a consequence, maybe it ends up with a stack smashing event. Maybe it ends up with a segmentation fault. Maybe I just get away with it and I screw up my own memory. Right? So be careful. What happens in Java over here? You can do this part. So you can't create static arrays in Java, but you can do something like this in Java. What Java is going to do is it's going to come in with its syntactic sugar, and it's going to convert this over to a dynamic array, which we'll cover here shortly. Right? So let's go ahead and try to access something that doesn't belong to us. There we go. So what's going to happen here? We don't have segmentation faults. We don't have stack smashing events in Java. It knows how big an array is. It knows that it's big, of size 10. It's going to say, well, that index is way out of bounds. And it ends up with an array index out of bounds exception. And it even tells you 10,000 is out of bounds. I know that it's of size 10 here. Right? You can only access 0 through 9. So same idea. You're accessing memory that doesn't belong to you or doesn't exist, but it results in a different error. And do you remember what kind of exception this is? I did not have to surround this with the try catch. Do we remember checked exceptions, unchecked exceptions? This is an unchecked exception, the good kind of exception, right? I could go ahead and try to surround this. Try, do this, or let's do this. Do it down here. Try and then catch a array index out of bounds exception. I'm not going to give that a name other than E. A-I-O-O-B-E. No, I'm not going to do that. And then to do something. There we go. There, now it'll just fail silently, right? Because I'm not doing anything with it. Right? So, be careful. Accessing something outside the bounds is bad, right? Accessing elements outside a valid array in C leads to stack smashing events, not exceptions, but segmentation faults, right? Or undefined bad behavior, right? Doing so in Java results in, and here I'm going to cut and paste that, an array index out of bounds exception. There we go. All right. So in neither language should we be operating with static arrays, because of course we don't want to abuse the stack here. The stack is small and defenseless. So we need to make sure that we're allocating it somewhere else. Well, I see stack here. What do you see? What else do you see? Heap, right? We're going to allocate it on the heap. Now, before we move on, stack, that brings to mind a very organized stack, a stack of dishes. First dish, second dish, third dish, fourth dish, right? What about a heap? What does that bring to mind? It's still a pile of stuff, but it's a little bit less organized, right? When I say heap, I mean a heap of, or like what, fill in the blank, heap of clothes. Okay, excellent. Laundry, right? Well, you don't have a nice organized hamper. What are you doing? You're just throwing them in the corner, right? And then it piles up. There's a heap of clothes over there, or a heap of garbage, right? It is far less organized, but it is much, much bigger, right? And therefore, you're not going to hit these limits that we had with static arrays. These are called dynamic arrays. Right? Dynamic arrays are allocated on the heap space, right? Which is much, much larger. In fact, there's no limit. Let me come back over here and see if it lists the limit over here. You limit all. Right. Max memory size, there it is. What does it say? Unlimited, right? That doesn't mean that you have infinite amount of memory, right? You can't download more RAM. Instead, it means that you can allocate as much memory as you want. We'll give you more. We'll give you more until we physically run out of memory. Right? Once you physically run out of actual RAM, then it starts persisting stuff to the hard drive. Once you've run out of virtual memory on the hard drive, the show's over. You're done. It's not going to be able to allocate anymore. Right? So it's much, much larger, right? Less organized, right? And consequently less efficient in some ways. Right? But you can allocate whatever you want on it. Right? In C, you allocate memory on the heap by asking the operating system, OS, operating system, for a chunk of memory, right, however big you need. So for example, if I want, say, we want to store, say, 10 million integers, right? We would ask for, how much memory would we need? For 40, megabytes aren't full numbers, so like 40 million, it's just slightly above that. So I only need 40 million bytes, right? 4 bytes each, int, right? I'll show you a trick for doing that here in a moment, right? You use the function called malloc, which stands for memory, and then allocation. There we go. So the M and the ALLOC, malloc, memory allocation. Right? And it has the following signature. Here's the signature. There we go. malloc signature looks like that. So some new syntax here. Right? First of all, size t is a built-in value. It's basically an integer. You can treat size t as an integer. In other words, you are asking for n bytes. Okay? The return value is a generic void pointer. Now that we've covered pointers, right, let's go back to what we were covering with pointers before. An integer pointer can point to an integer. A double pointer can point to a double. A character pointer can point to a character. What about a void pointer? Void, you might think, well, wait a second, void is nothing, right? Void function returns nothing. So maybe a void pointer points to nothing. It's like null. Nope, we already got something for that. It's called null. A void pointer is a generic pointer. It points to a raw chunk of memory, right? Here's my memory. First element, second element, third element, fourth element, fifth element, right? And dot, dot, dot. Right? It points to any one of these locations. It doesn't care that an integer is stored there or a double is stored there or whatever. It's just a raw memory address, right? So a generic void pointer is a raw memory address that can point to any type. And there's a good reason for this. I don't want to have a function to allocate memory for integers, and then yet another function to allocate memory for doubles, and then yet another one for characters. And then later on down the line when I define my own types called structures, I don't want to have to rewrite the entire malloc function to do it for that one, and then introduce another type, student type, or bank account, or airport location, or something like that. Anytime I create a new type, I would have to create a new malloc. I would have to repeat the work that's already given to me in the standard library. So the way that they solve that is by returning a generic void pointer. You just want a chunk of memory, 40 million bytes. I don't care if you use that for 10 million integers, or 5 million doubles, or 3.8 million whatevers, right? Here's your memory. Here's your chunk of memory. You use it however you want, right? So the returned memory can be used for whatever type you want, right? This means only one function is necessary, right? When you get the pointer back, you cast it to the proper type, right? So when I get this pointer back, okay, now I'm going to make it point to a bunch of integers, or now I'm going to make it point to a bunch of doubles, or foos, or whatever it is. Yeah?
So it can point to how much or how little memory you want and so on?
Yep, you could, well, I could ask it for like 1 byte. I could ask it for 4 bytes. It's going to give me at least that much, because it is really inefficient to say, just give you 4 bytes, right? And then what it's going to do is it's going to give you an entire page of memory, a page segment of memory, and whatever the page size happens to be. Let's say that it's 1 kilobyte. So it's going to give you, oh, you only want 4 bytes. I'll give you this entire 1 kilobyte. Yeah, okay, you're only going to use the first 4, but it would be more inefficient for me to only give you this little tiny space and then this other chunk to somebody else, right? It's not going to cut up memory that finely because it's really inefficient. In fact, it's called fragmentation. And you don't need to do it too much on modern operating systems, but has anybody ever defragged their hard drive still? Okay, 1 or 2 of you, right? Why? Because files are stored all over your hard drive, right? And that means that access this one big file, it's got to read this part of the hard drive, and it's mechanical, so the other part of the file may be completely on the other side of the hard drive, physically, right? So what you want to do when you defrag it is you want to collect all those files in the same location on the physical location on the hard drive, so that it's not, going back and forth. That's really, really inefficient. So it's really, really inefficient to chop up memory like that so finely. Right? All right, so let's go ahead and write some code to show you what I'm talking about here. So I'm going to have an integer pointer here, int array. It's always best practice to initialize this to null if you don't have something to initialize it to immediately. That pointer is no longer going to point to one integer. It's going to point to an array of integers. Okay. How do I do that? By calling malloc. ARR is equal to a call to malloc. There we go. Now, how many bytes do I want? Well, first of all, let me go ahead and store that into a variable here. Let's keep it small for now. 1,000 integers. Okay. How many integers does it take, or how many bytes does it take to store 1,000 integers? 4 times 1,000, 4,000. Right? But it is a terrible practice to write it like this, right? Because first of all, I want it to be variable, right? So let's go ahead and change this to 4 times 1,000, right? There's my math. And I take this 1,000 and I've got that stored in a variable, so let's use a variable there. And I still don't even like this, because here's a dirty little secret of C. Not all integers, the C standard does not say that the bytes are, or that an integer is 4 bytes. It says that it's a minimum of 2 bytes. So if you take your program over to a system, an ancient system, or an embedded system, really weird system, it could be 2 bytes. It could be 3 bytes. It could be 4 bytes. You could go in the future, 50 years from now, and the standard integer type is now 8 bytes. Right? We don't want to hard code it to 4. So what I'm going to do is I'm going to ask the operating system, how big is an integer? What is the size of an integer? Right? This size of is a macro that will take int and it'll say, okay, well, on this system, it's of size 4. Right? On this system, if it's a double, it's of size 8, if you spell it correctly, et cetera, et cetera. Right? I want integers here, so I'm going to say that it's an integer. Now, it gives, remember, it gives a generic void pointer. I want to force that void pointer to become an integer pointer. So I'm going to typecast it as such. Int. You remember you did this in your first couple of weeks with integers, because if you divide 10 by 20, you get 0. So if you force one of those things using a typecast, double, right, to become a double, then the truncation doesn't happen. What I'm doing here is I'm forcing that generic void pointer that can point to anything. Now it knows that it's pointing to an integer. Right? There we go. And I can use it just like any other array now. Right? You can now use it as a regular old array. So ARR sub 0 is equal to 42. ARR sub n minus 1 is equal to 101. And I can print them out. ARR sub first and last, %d and the line, ARR sub 0, and ARR sub n minus 1. There we go. Remember, my heap space is now unlimited power. Right? There we go, and it works. If I bump this up to 10 million, it will still work. 42, 1,000. Remember, it didn't work before with static arrays, but now it works because I'm allocating it on the heap, which is much, much bigger. Let's edit this code and do the same thing, but for a small array. I'm not going to make 10 million because it would not be able to render. Star ARR. I don't have to set it immediately to null. I can just go ahead and immediately call malloc. Right? And let me put it into a variable, int n is equal to 5. There we go. 5. And how many do you want here? I want size of int times n. Right. There we go. And by the way, oops, I don't want to save the web page. Out of habit there. What is stored in ARR right now? Same question as before. Same question as before with the static array. What's stored in it before I do anything with it? Garbage, dead beef, uninitialized memory. Right? Let's visualize this. Right? This should work now. There we go. Now, when I allocate it, first of all, I've got 5. When I allocate it, it's not going to be in the stack. The pointer's in the stack, but what happens when I actually execute a call to malloc? A brand new array is created on the heap, and it can hold 5 elements. Same as before. Right? It's exactly the same. It's all contiguous. It's all chunked together, but now it is on the heap, and it is much larger. It is unlimited. Effectively unlimited. right? What's the largest value that I can do for an integer? 2.147 billion. I think I can get away with this. Oh, nope. It's not gonna so it says unlimited, you can ask for it, right? But you ain't necessarily gonna get it, right? 2 billion, that's what? Times 4, that's gonna be 8 billion, that's 8 gigabytes, right? Thereabouts, right? So it's not gonna let me do that because it's too big. How do I know that it's too big? Right? So if malloc fails for whatever reason, it returns ... So it returns a pointer. What is the only pointer value that you can check for invalid? Does not exist. Null. It returns null. Right? So if array is null, then the allocation failed. Printf memory allocation failed. Download more RAM. There we go. That's all we can do. And then exit. So if malloc fails for whatever reason, it's going to return null. But otherwise, this is how you can use it. All right, 10 minutes left. I can give you that entire presentation again in Java in 2 minutes. Let's do a dynamic array in Java. Int n is equal to 1, it doesn't matter, 1000, let's say. Right? So int array, right? I'm not going to specify how big it is. Instead, I'm not going to call malloc because there is no malloc in Java. Instead, I want a new array. So I will use the keyword new, int n. There we go. It looks very, very much like malloc, right? In fact, if I got rid of the new, I called this malloc and I changed it into a function call instead of the square bracket notation, it would be exactly the same. In fact, let me go ahead and copy everything over. Right? Once I've got this, I can go ahead and just treat it as a regular old array. Right? System.out.printf. There we go. 1000 works just as well as 1 million. Works just as well as 2147 billion. There we go. 8 gigs. It's not that big. I think we can do it. Okay. What happens when you run out of memory over here in Java? It gets an actual JVM error, out of memory error occurs. Right? So, nope, can't do that. You can try and catch this, but there's really no recovering from it. Right? So that is dynamic arrays in Java. Right? All you need to do is use the new keyword. Let me copy this over into Java, or into the notes. Java. There we go. So one last thing that I'll do here is, what if you don't want integers? What if you want doubles? What would change here? Let me kick this down to 1000 so it works. You no longer have an integer pointer. What do you have? A double pointer. You don't force that void pointer to become an integer pointer. You force it to become a double pointer. You don't want 4 bytes. You want however many bytes a double takes, which I know is 8, but I will let the system do that for me. Right? After all that, you can still treat it like a regular old array. There we go. And this will be %f and %f. There. 42 and a half, 101 and a quarter. How do you change it over here in Java? Once again, you change the type. Double. And double. Oops, double. 42.5, 102.25, %f and %f. Exact same. All right. So when we come back on Wednesday, we're going to cover a little bit more on on bookkeeping and memory allocation and cleaning up after yourself. But over here in Java, this is the last time you're going to see me ever use an array. They're terrible. They suck. Right? So what we're going to do is we're going to move immediately on in Java to dynamic arrays, not dynamic arrays, but dynamic data collections. A list of integers, right? My list, or A, I'll just call it A for now. Or a set of integers, B. Or a map of integers mapping to integers, right? I'll call that one M, right? Now it's not compiling here because I need to import everything. Java.util, Java.util, Java.util. With both static and dynamic arrays, what happens if you create it and it holds 1,000 elements, it can only hold 1,000 elements. What if you only put 5 of them in there? You're wasting this entire space. If it holds 1,000 and you need 1,001, what happens? You need to create a new array because it's only holding 1,000. These are all dynamic data structures. They will grow and shrink automatically when you put stuff into them, take stuff out of them. A list is ordered and allows duplicates. A set is unordered and does not allow duplicates, but a map blows them all away because you can map anything to anything, right? You're no longer bound by a bunch of index values. You can map strings to integers. You can map integers to strings. You can map strings to strings. Christopher gets mapped to Chris, a shortened nickname, right? You can do whatever you want with a map. You can map whatever piece of data you want to whatever other piece of data you want. And it is extremely powerful. And this is why I won't even talk about arrays in Java anymore. Once you can afford these things, right, you never go back. Right? In fact, a lot of programming languages like Python, they've got lists, sets, and maps built in. They're not really maps. They call them dictionaries because they're kind of neutered maps. But anyway, they don't even have arrays. PHP, Java, JavaScript, Python, they have things that look like arrays but are not arrays. Under the hood, they're all lists. And actually under the hood of that hood, they're all hash tables. Right? So once you've got these, well, you're in business. Over here in C, unfortunately, we don't have them. We just have regular old arrays. All right, we'll continue it there next time.